Okay, but now we can start the afternoon session. So it's about to have Simon Ekhammar, who's going to tell us about integrable regular trajectories of any force again.
Thank you so much. So it's a great pleasure to be here. Let me just start by thanking the organizers for inviting me or giving me the opportunity to present some of the work that I've been doing. So I'll talk about work together with Nikolai Gromov and with Ekhammar, who I suppose are people that many of you know. They've been around for a very long time. So this is based on two papers that we've been able to write so far, but it's something that we're kind of actively working on, something we want to do more. And it's a topic I'm just very happy to present. And if you see anything that you recognize or have some ideas, I would love to hear them, of course. That would be fantastic. So let me start by sort of setting up the talk. If I can. There we go. Change the slide. So the topic, as the title sort of gives away, is about N equals 4 simply angle. So this is a topic we have had a few talks about already in the conference. But let me just start by recalling the sort of basic facts that will be important for me. So N equals to 4, four-dimensional gauge theory, there's supersymmetry. I have a coupling constant. I will always work in a planar limit, and it's a conformal field theory. Now, this coupling constant, I can of course tune. And if I were to tune it to be weak, I would go into a sort of regime which is well described by perturbative gauge theory. I could equally well tune the coupling to be large, and then you would expect that the sort of the description would be strings on ADS5 times S5 in this case. So the one thing I want to highlight in this sort of picture is that integrability, of course, is present for all values of the coupling. This is usually how I start because I think it's a beautiful, remarkable fact that we should be able to compute things starting from weak coupling all the way to strong coupling and in between. Now, presumably, at least I hope, that integrability will allow us to completely solve this theory. I think it's fair to say at the moment that we're not there, that the most powerful techniques are so far only really about the spectrum. So by the spectrum, I mean that we can compute the conformal dimension, or we can compute two-point functions in this theory. And everything I will say today will be about computing the spectrum. So computing the spectrum N equals to 4, two-point function local operators. Local operators are built out of letters. Those letters are a set of fields, and fields are controlled by the algebra that underlies N equals to 4. So for example, we have the scalar field, the 6 scalar fields on N equals to 4. So how do you do this practically nowadays? Well, the most powerful tool to do any sort of computation with the spectrum is to use the quantum spectral curve that people have mentioned every now and then in this conference. And this talk will be about trying to use the quantum spectral curve to the full extent and use it to explore the spectrum of this theory. So maybe for those of you who don't work with QC on a daily basis, usually it's a good place to just start to briefly recap what the QC is doing at the moment and what it has done. Of course, the QC didn't just come out of nowhere. It's the sort of currently the end result of a very long line of development, starting with the seminal work of Joe and Kostya, but of course many others. And that this work eventually evolved into the QC. So this is great. It's great that we have come a long way. It's a bit unfortunate because the formalism is usually built on intuition, built on various things that came before, which can make it a bit hard to understand it at certain points. And that's just something we have to live with. So before I start trying to explain any of the components that make up the QC, let me just show essentially what you do with it. So let's look at the local operators. And here's a typical plot. People will show you for the local operators at the moment. This is from a paper by Gromov, Nika, Julius, and Arpad. I think the reference is not there. Sorry. So the things I would like to highlight on this picture is, of course, that we have different regimes that are of particular interest. So if I send the coupling all the way to 0, I will go into this pinching regime, this perturbative gauge theory regime that I talked about before. And around this point, we can solve the QSE perturbatively, analytically at the moment. And there is fantastic algorithms by Dima and by Christian that allows you to essentially just plug in and work this out. And this should, in principle, work to arbitrary order. The thing that puts a cap on this is simply your computer power. Now, if you want to go to strong coupling, in general, we struggle at the moment. The way we do it is through numerics, most mentioned by Shai, for example. And so we run numerics, we start from this weak coupling, and we see what happens. Of course, there's still great results from coupling, but the string regime, this regime here it's still difficult. This is something people work very actively on, trying to understand. So the sort of benchmark result by the moment is the Konishi operator. And by using numerics, we compute it to 1/λ to the 7/4 at the moment. So this is not an analytic computation, this is from fitting numerics. All right, so this is a sort of typical story. People will tell you about how to use the quantum spectral curve. So in this talk, I will try to do something that is slightly different and not work with local operators. So to kind of showcase this, I'll go slowly through some typical pictures. And these are pictures I will use throughout the talk to depict what's going on. So here I have plotted some data points, and I plotted the spin on my y-axis and delta, my conformal dimension, on the y-axis. So the different colors here have different values of the coupling. The local operators, of course, will sit along these horizontal axes. So if I want to kind of get the plots that I showed you before, what do? I zoom in on a set of data points, and I don't plot S against delta, I simply plot delta against G. And if you want to, this is exactly the sort of problems people usually solve. So for example, if you solve a beta ansatz, this will be the prediction. And you see it fits fairly well with the data points. The data points are exactly the C data points. The curve here is just the first approximation to those points. Now, I don't want to study local operators in this talk. I will try to go to continuous spin. So how do I go to continuous spin? I need a prescription. Well, I will tell you what I'm doing, and what I'm doing is I'm using the numerical quantum spectral curve, which allows me to plug in not just S integer, but essentially any value of S. And then I simply continue numerically. So I sat down and I did this a few weeks ago just to check that it works. And the picture that emerges looks like this. So now each and every line is a different value of the coupling. And what you should notice in this picture is that there exists a certain regime that looks especially interesting. And it's this part. Yeah, please.
What you said about the continuous spin, is it computational or conceptual, in the sense that do you give any importance that S could be a continuous number?
So I would say, well, I guess you can answer it yes in both ways. So let's start with the computational way. In the computational way, the way it works is that you have certain asymptotics, this QSC. One of them is S. And you simply say this asymptotic is now not an integer number. It's something else.
But this is for big values for S or any S?
Any S. So you see here in the plot, of course I have kept S before. That's just because I got tired. And because I wanted to show you what happens around S equals to -1. I can run it for any S. That's not an issue.
But the non-integer values have any significance?
So the non-integer values have significance in various different ways. So for me, first of all, the way I want to do is to try to study what happens here and try to understand what this can describe this region. Now, the natural thing to think about here is that this should be some non-local operator. Now, I would love to tell you exactly what this non-local operator is, and I can't do it at the moment. It's presumably like a Leicht transform of these local operators here in this regime. Here it will be a different non-local operator. The reason I can't tell you is because I'm using this framework, QSC, which is functional equation, that doesn't require me to tell you what the operator is. It only is based on symmetry. Thank you for the question, for the opportunity to say a few more words. So to study this regime is something that people have done a long time. And there's been a lot of work trying to understand this regime. But let me zoom in here and tell you what I want to do. So now instead of studying delta as a function of G, I want to study S as a function of G. And I want to fix my delta to be a specific value. And to be in this horizontal trajectory, I would fix delta to be between -1 and 1. And then here I've just plotted S as a function of G. So what I do is I compute fluctuations around this horizontal trajectory. So people have done this, and this was done essentially in QCD the first time around. So this is the BFKL kernel, which is the answer that's known for.
So one of these operators should be the BPS operator, right?
Yes, yes, beautiful, of course. So you see the BPS is distinguished, right? It's right here. So the BPS you can see because all lines have to go through it. So it's coupling independent, right?
Okay, yes, for all G, okay, yeah.
So it's the one point where they all like merge together. And it's a great question. It's something we'll come back to. Something that really distinguishes things is that they do pass through this point. That is not true for some arbitrary trajectories. This is one of the things that makes it extremely much simpler to study this particular trajectory. So if we look at this, I got it numerically, and then I checked that it matches the prediction, which it of course does. So what I would like to tell you in this talk is that we can compute these numbers nowadays through a beta ansatz-like method. And the claim is that we can compute exactly this S of G using a combination of beta and Baxter equations. And the goal would be to present these equations to you and tell you their validity, how we can use them, and how we can try to go beyond.
You could explain why this thing is horizontal?
Why it is horizontal?
Yeah, there's some obvious meaning why that.
In truth, I won't explain it, no. In general, the idea would be that you should study a local operator, it's like a local operator which will have these properties. But at the moment, there will be an observation that this happens.
But this blow up that you're showing is the corner, right?
So thank you.
So it's not the sharp, there is no sharp corner.
There's no, okay, that's a fantastic question.
Analytic.
This is of course only sharp, strictly speaking, at zero coupling. At zero coupling, this would actually, you can just think about it as passing through, and there's another trajectory going like this. And what happens with finite coupling is that these mixes. So it's when you turn on a little bit of coupling, it's of course no corners. What I show here is not quite the corner. So you see I plotted here delta 1 over 2, so I'm sitting here. We can also study the corner, but this is significantly more complicated, but it works as well. Actually, studying the corner is extremely important. So just history of integrability, this is one of the places people studied these equations, and they figured out that the asymptotic beta ansatz only works up to 4 loops. So what I will talk about in this talk is mainly generalizations beyond this. So other sort of horizontal trajectories. So there's two ways to sort of generalize this in a natural way. One is to go even further in S. So this is exactly the same sort of picture that I showed you. It's just that I continued even more trajectories that would all lie at the same surface. And so this is the region I showed you before. But for example, if you look below, you see that there's a ton of different trajectories that's going to show up. So the sort of simplification and simplicity of the first trajectory is really because we're studying the absolutely simplest example.
Well, why is this thing called the Pomeroy? Like,
Because it matches the Pomeroy from QCD. So the idea is that by maximal transcendentality, you should be able to compute Pomeroy eigenvalues from this, right? So they will match from QCD and n equals to 4.
does it match exactly?
The maximal transcendental piece matches exactly as far as somewhere. Not the entire thing, of course.
So this is a non-local.
Yeah. Unfortunately, the methods I will use won't tell you much more than was already known in the literature for the Pomeroy. But they will tell you much more about non-higher twist visualization. Another sort of immediate generalization is to say that, okay, you looked at some specific set of quantum numbers, why don't you look at different quantum numbers? And so just as a recap, n equals to 4 has 6 quantum numbers. There is the conformal group, there is the R symmetry. The thing we do here is that we keep most of them fixed. And we use the other two as parameters in these sort of plots that I've shown you. So what we did before was that we looked at these sort of typical examples. And I will use this sort of notation, which I write trace of nabla S to Z to the L. This is a highly imprecise notation. It only means that these surfaces contains these local operators. They contain a lot more. But they're useful to think about, useful to have some sort of picture in mind. So before the sort of surface was traced to the delta S and then Z2. And the idea is that I will discuss both of these generalizations, and the tool will be this asymptotic backstream betas. So I want to just show you what it is, to see what the structure is, and I figured that the sort of best way to do this would be to consider the normal asymptotic beta answers and just put them side by side. We'll see what happens, and hopefully, by analogy, many of you will see essentially what's going on. So the standard ABA, what does it do for you? It computes the conformal dimension. So the most famous example of this is that you simply compute an SO2 sector, and it's given by this set of beta equations. So here you have your conformal dimension. It's given as some sum over roots, usually called beta roots. It's an equation that's only true up to wrapping. And the thing that fixes these beta roots is beta equations. And the beta equation is given as an equation essentially on the S matrix. Now, if you want to generalize this, you just have to go beyond SO2, BSU2,2/4, and you write down an algebraic equation essentially for each and every step, each and every node on the Dickey diagram. This is the standard picture. So the ABA computes spin instead of delta. So let me give you the example of the SO2 sector, which is exactly these sort of horizontal trajectories I talked about before, with a simple set of quantum numbers. And the formulas are almost exactly the same. So now I get a formula for S minus some bare dimension, or some bare spin, given as the sum of the roots. And these roots are fixed by a set of beta equations. And these beta equations involves something that looks like an S matrix. And the equations are once again only true up to wrapping. So this is only true in some perturbative regime. After that, you would have to extend to either the full QSD or come up with something more advanced like Lucia correction. And the S matrix is curiously similar to massless modes, medians-free, times-free, and T4, which is just, it's basically a fun fact. I should say that this S matrix is significantly simpler. So I think Alessandro said you have to hit your head against a wall for 2 years. Here you cut it down to maybe like 2 months or something like this. So it's a nice place to be if you want to get quicker progress. Now, the reason we call this ABA and not just ABA is because we do exactly the same sort of thing. We extend this SL2 to the full structure, but now we're not able to just write down algebraic equations for each and every node. We need 2 nodes that we have functional equations for. Essentially, what happens is that we cannot parameterize all this function that appears in terms of just roots, but as functions. Yes.
What is that? What is like in the same way that we have like be like some related to critical functions, but this beta roots now.
I will
One.
exactly. They will look exactly like beta roots. So later in the talk, I'll try to show you where beta roots appear normally in the QSC, and I'll show you how the sets appear in the QSC and the sort of difference between them. Of course, I don't have an operatorial description of how to get these equations. I only derive them from analytics. And you have to supplement this with an additional math equation. Yes, please.
By Baxter equation, you mean TQ?
Yeah, yes. It's a beautiful equation. I can write it down if you want to. It's exactly what you would expect. It's sometimes life is not that. So it's like let's see. So in the absolutely simplest case is actually just the standard for Baxter. This would be if the G strictly equals to 0. And then the generalization here is that if you want to go to non-zero G, you have to add in-humps here and here. And then this will be true for the absolutely simplest sector, which means you can actually solve it exactly. But then when you go beyond that, it won't be solvable exactly, and we don't know how to do it except numerically.
Can you write like the full structure as a Baxter equation, just a bigger one,
You
or
mean
a system of Baxter equation?
for everything?
Yes.
Well, you can certainly rewrite each and every beta equation as some sort of extra equation. If you want to rehash everything, in a sense, you can, I think you would call that QSC at the end of the day. So I'm not sure if how much more useful it is. To the best of my knowledge, this rewriting is the best I can do in presenting it in a manageable way. But it's an interesting question. I don't have a good answer. So let me give you some motivation before I jump into the rest of the talk. So this the sort of like motivation that. Oh, sorry.
No, I was just thinking, so at the beginning you were talking a lot about analytically continuing the spin to
Yes.
real values. So is that something you can do at the level of these equations already? Because, I mean, on the right hand side, it will be tricky because there's the sum. So that would be pretty non-trivial to make S real.
Sorry.
On the left, sorry. Yeah, on the right,
Yeah.
maybe it's quite natural, I think.
So you wanna, what is the, so these equations here are only valid exactly as fluctuation around this horizontal trajectory.
Yeah.
That's what they're describing. If you try to go beyond this horizontal trajectory, these equations are not good
Right,
anymore.
here's the fluctuation.
It's really only perturbatively around that horizontal trajectory you do this. If you want to go to a local operator, you do this, right?
And how does it behave for large S?
For large S, well, this is famous that it goes with log of S and you get the cost and so on. I won't have much to say about this.
So is it true that this trajectories become flatter and flatter if you go for larger L?
For larger L, yeah, I think it's actually true. I will show you the equation later, and there's a 1 over L plus 2 that expression.
Because I mean, what is the regime of the variety? You know that the asymptotic the transverse breaks at G to the L.
Yes.
And what about?
Yeah, beautiful. Thank you. I didn't write out exactly what they did at the bottom. The reason is that you can estimate this. So okay, let's remember. So in ABA, I think it's 2L plus 4. Like the 4 is from supersymmetry, right? And then 2L is because the perturbation theory goes in G to the 2. Here it turns out it's valid up to G to the L plus 1. 1, I think could be supersymmetry, but L is essentially the length. So that is the validity of these equations. It turns out to be a little bit better sometimes when you go below. So just as a good example of this, the Pomeroy that I showed you before is L equals to 2. It means it's valid to G to the power of 3. There is no G to the power of 3 term. All I can do is predict G to 2. But as I go to higher and higher length, I can do better and better. Try to show as much as I can. Okay, so for me, motivation is basically study integrability, try to understand as much as we can about any form, and try to find new places where we can do analytic things. This is to be extremely non-trivial in general. Of course, daydreaming would be to understand these non-local operators, try to make contact with detectors, with light trend transform, try to understand conformal Regge theory, go for all the OBE coefficients. I think both are good motivations, but this talk will certainly stay in the first one. So I have divided it into 2 parts. The first one is just going to be about these minimal sectors that I showed you. I'll show you essentially where various things appear, and then some results. And then part 2, I'll do some generalization and show you how the big structures. All right. So let me go into the minimal sector. So I'll start by explaining what happens to you when you increase L, which I think is a good first thing to just see. So now I will plot everything for a fixed value of G. And since I want these for a sample trajectory, I need G to be small. And small for me in this picture will be 1 over 50. So the first picture is the one we've already seen. This is the Pomeroy-like trajectory. Now, if you go to L equals to 3, this turns out to happen. And so the one thing I really want to emphasize here is that when you go to higher length, you're going to have more and more of these horizontal trajectories. And then, if you go to length equals to 4, turns out you get even more. So there is a richer and richer structure as you increase L. And it's some sort of very beautiful thing from the point of view of integrability that these different trajectories, when you analytically continue them, they go to local operators that are far in perturbation theory from each other. So it really is you finding a different regime where things come together and talk. So it's some sort of statement of integrability of the full theory, not just perturbative around some local operators.
Oh, wait, we're sorry. You answered this question before, but I'm still confused. Like,
Yeah, please.
what is the physical observable you're studying? I mean, it's like, are you just kind of like analytically continuing to non-physical values and hoping this means something? Like,
Yeah, that's sometimes true, right? So you would have to go to say confounded Reggie theory or something like this, in which you would learn that this is important, right? To compute p coefficients or similar things. There's data point approximation. Say computing the intercept will be the thing that determines.
no, I'm saying, but yeah, like even in the best case scenario,
Yeah.
what would the actual physical observable be that you would be studying based on looking at these weird negative values?
Okay, so let's take a good example. I should have done this maybe earlier. I don't know if this is the best case scenario, but for example, this piece here resums perturbation theory extremely well. So it means that if I can know this function here and perturbative exponent here, I can know a lot of things about these local operators. I would get predictions that goes much higher in perturbation theory, although it will only pick out maximal transcendental things usually.
Oh, wait, so perturbation theory and what?
So if you do perturbation theory in the coupling here,
Yeah.
and then just analytically continue and expand around this point.
Okay.
That will give you one set of data. But you can also do, if you know the solution here, you can do the same thing and try to match. And that will teach you about higher loop results, for example. I guess this explanation was awful. I'm happy to show you the actual equation for what I just did.
No, but don't you already know the perturbative results any order you want?
Uh,
I thought the whole challenge was to get strong coupling. I mean,
Well, okay.
perturbative results very well.
So I will show you a bit. Okay, one question is to get strong coupling, that I agree. I don't think this will help much with strong coupling at the moment. But at least at strong coupling, we will see some emerging features of things that happens. I will admit that the main motivation at the moment is to simply see how we can describe this regimes, to see what sort of structure this is there. Right. So all these plots are for fixed R symmetry, and they only vary this delta f. So let me just kind of quickly describe for you how you actually find the equations that I showed, and where all these different objects fit. So to do that, I kind of have to introduce accuracy. And it's always a great challenge to know how much one should say, and how little one should say. So I'll try to find some middle ground. So I will simply briefly tell you that the QEC is a collection of a lot of Q functions. They're all related using finite difference equations. Now, among these Q functions, there's a set that is especially important, that is called P. And these P are all functions of a complex parameter U, usually called a spectral parameter. Now, the asymptotics of these P encodes the quantum numbers. In particular, they encode the R symmetry. Now, the most important part about these P is that they have a very specific analytic structure. So the analytic structure is that these P's are functions with a shortcut. Now, if you have a function with a shortcut, you can of course ask yourself what happens if I analytically continue. So if you take these P and you analytically continue, you end up on a different sheet. And this different sheet, there is an infinite number of cuts. So in principle, this looks worse. This looks like the task now will be to analytically continue for each and every one of these cuts, or at least find some nice way of describing it. The statement of the QSC is that all these cuts, all this procedure of analytic continuation is encapsulated in a few simple set of equations. In particular, the analytic continuation of P, so analytic continuation is this tilde. It's just simply multiplication of P with a matrix mu. Now, if I introduce some new object, I should also explain to you how to fix this new object. And so there exists a set of closed equations, also for mu, and for how to analytically continue mu. And here are the equations. And this forms what people call the P-mu system. So this is a very sort of compact way of representing the QSC as a set of these P with these analytic properties and this mu. You have to constrain them with these Riemann-Hilbert problems. The one thing that is lacking from what I told you is, of course, where the conformal dimension enters and where the spin enters. The P only encodes the R symmetry, so I still have to tell you how to read off the conformal charge. And that sits in the asymptotics of this mu function. it sits in the different components of this matrix. Now, it matters a little bit in which regime you are to know which asymptotic each and every component has. But for local operators, it turns out to look like this. So if you know mu12, you can read off delta. And luckily, because life is simple, if you are in the BFKL regime, it's exactly the same component, and you can read off S. So this is the name of the game. You find these functions, you constrain them according to their analytic properties, you solve the system, and you read off delta and S. So let me tell you what happens when you take these horizontal trajectory and you try to analyze the Qs. So here is once again this picture of this twist-free surface. So if we look at the point where spin is equal to 2, so that's the red dot up furthest, you will see that this happens. So you take a look at this point, you plot your function mu, and it turns out that mu exactly encodes the beta roots that appears in the asymptotic beta alpha. And so the name of scheme of ABA is to simply find these roots, and from that read the anomalous dimension. So what you do? Well, if you know this is true, you try to do the same thing, right? So we took this, we numerically solved it, and we looked at what happened to mu. And what happens now is that there are still roots, but they all lie on the exact cuts. And because of this, they will also extend up and down in the complex plane. So these roots are exactly the sets that I introduced before. And so the name of the game is to find these sets. Typical way to do this is that if you have a cut, inconvenient, so you blow it up on the unit circle. And if you do so, your roots will sit exactly somewhere on the unit circle. The one thing I have to tell you is how to actually fix these sets. All right. So fixing this set of K is exactly solving the ABA. So I showed you before the sort of structure that emerges where I have various beta equations, I have some Baxter equation, and I have some beta equation. Now, in the particular case of the minimal sector, life is as simple as possible. So all the beta equations on the left-hand side turns out to be trivial. The Baxter equation turns out to be exactly solvable, and the masses equation is relatively simple. To actually derive all these things, you have to go through some QSD and just work. But at the end of the day, this is what we found. And of course, if you want any sort of technical details, feel free to come ask me, or look in the papers. So this is what it simplifies to at the end of the day. So this is the same equations that I showed before. Now, I had this S matrix, and the S matrix takes a specific form, and so the form is fully explicit. And so the S matrix has a third factor of gamma functions. These gamma functions are exactly what encodes the conformal dimension. And then there are some other pieces that are given by objects that are well known to people who have worked a lot with the asymptotic beta alpha. So there's one piece, which is simply the standard scattering phase, the best phase. There's another piece that looks like scattering phase from Wilson loops. Hopefully this is some sort of sign of a non-local operator. There's a Wilson loop in the picture, but we don't have an operatorial description of it. And so this is what you have to solve and plug into your computer. Or do it by hand if you want to suffer one. So let me show you what happens if you actually solve it. So I will do it in the simplest possible case, which is when I impose additional parity symmetry, just for simplicity. In that case, there's only two independent groups. And I'll take the coupling to 0. And it turns out that all these factors basically become 1. And so at 0 order, these roots that were living on the unit circle simply becomes roots of unity. And they become roots of unity. And there's more and more choices as I increase L. So I can try to just simply plot whatever options this equation allows me to do. So if I take length 2, there is only one valid solution. That's good. There was only one trajectory for L equals to 1, as L equals to 2. L equals to 3, I find 2 different solutions. L equals to 4, there's 4 solutions, and it keeps going. And if you want to, you can simply plug these things in as you find the root conservatively, and you find a closed formula for the form of spin as a function of delta. And so for the simple horizontal trajectories, this is the answer. And this is of course only valid supporting perturbation theory, and in this case I've just written it down to g to the power 3. Pushing it further is possible, but then it's better to do it on a case-by-case basis. So just to try to be sort of clear about what was accomplished, let's look at these pictures again. So for one horizontal trajectory, the fluctuation around this horizontal line is simply given by -4 g squared and this xi here. So xi is given in terms of polylogs, and that's it. For spin free or twist free, sorry, there's two trajectories, and here is a nice feature, which is that this perturbation theory now starts as order g instead of g squared, which is something that people usually don't see in n equals to 4, but something people have seen a lot when they work with masses most in ADS3, for example. And then for 4 horizontal trajectories, there's 4 solutions, and they take this particular form. And just to showcase what sort of numbers will appear, let me solve the equations and just take them at the intercept point, so delta equals to 0. For L equals to 2, I can't do much better than what I already showed you, because the equations are only valid up to g to the 4. So this is the result. For L equals to 3, you can push it a bit further. So now you have it's valid at least to g to the 4. And you start seeing a bit more fun numbers, like zeta 3 and various powers of pi. And for example, L equals to 4, the expression starts getting extremely messy. But we took this, we ran high precision numerics, and we verified perfect matches with all of these expressions. So the method seems to really work to high order perturbation theory. Right. So this, what I showed you, is sort of the simplest case. This is essentially trying to solve the vacuum, so to speak. So how do we do better than this, or how can we do more? Well, this is the sort of idea of trying to do this for any sort of trajectory. So let me first briefly recall this picture I showed before, which is this whole surface. So I showed it before, but here is what it looks like. So this is us computing the exact Reggie trajectories for the surface that includes the polymer, and going far beyond s just -1. And so this we did numerically with QSC. So let me highlight a few areas. So there is the first horizontal, which is what I talked about before. There's the second horizontal, which is simply lower down, which has even more trajectories, much like higher length. There is branching areas. That is the area where the operators coming from the local meets the horizontal. And there's also reflection areas, which is where essentially two D-left lines will meet and mix. And what we claim is that eventually we will be able to describe all of these things, both quantitatively and qualitatively. But at the moment, I will try to just talk a bit about what happens at the second horizontal trajectory. So let me just once again come back to the structure of these equations and just show you what they actually look like in their sort of full glory. So to describe arbitrary trajectories, I need full PSU 2.2/4 symmetry, and I need my massless mode. So the ingredients are simply roots. So I attach roots to 6 of the nodes, including the massless mode. And then I have 2 non-trivial Baxter functions, Q2 and Q6. And then there's a whole soup of different resting phases. And I'll use this sort of notation where beta means algebraic equation and Baxter means functional equation. And if you want to change the charges, or if you want to do different things, what this corresponds to is you changing the number of roots or changing the asymptotics as the usual beta ansatz. And then this is what we found, and we write down all the equations. So this is the set of equations you need to solve. And if you have seen EDA equations before, you will recognize that they look extremely similar to the way local operators look. The different pieces are essentially the ones that we have written out in blue. So what it looks like structurally is the standard asymptotic ansatz, just coupled to a new set of particles that also can scatter with everything else. Much like it would look like in ADS. And then we need one additional equation to fix these additional ones. And then finally, you solve these equations, you plug it in, and you read out the spin. So that's the name, that's the game, and you just have to do it.
So the number of z's is fixed here. You said
Yes.
that it's 4, or 6, and so on. What if you take less than less z's? Does it describe anything?
Yes, that's a good question. So let me go back, actually. So it turns out that in all the cases we study, for the horizontal trajectory, we have exactly 4 sets. But for the reflection area, we only have 2. There is a sort of idea why there's always 4 and 2, which goes back to you looking at how analytic properties look like for these functions. We hope that one should be able to generalize beyond and have more sets somehow. We tried to make it work and find numerical solutions, and so far we have failed. This hopefully would correspond to doing different sorts of analytic continuations. But so far nothing works. So this is where we're at the moment. So as an example, here's the second horizontal trajectory. So here's the same picture again, and just me writing out that in this case, you have to solve for 4 massless roots, but also 2 massive ones. And what you do is you solve and you find exactly this sort of picture. And so here there are 6 trajectories. We couldn't solve everything analytically, but we could solve it numerically, and you find some nice results. In this particular case, while I couldn't solve it analytically, I could solve it numerically to such a high order that I can just guess what the numbers are. Once they start matching with 20 digits, you stop being afraid. For L equals to 4, the second trajectory is quite complicated, but we managed to solve these equations, and then we use them to start up numerics. And in that case, you will find this picture. So things start to become extremely messy. So this is 30 different trajectories, all mixing together and interplaying with each other. So the just sheer time it takes to generate these pictures is one of the main sort of bottlenecks of doing these. But even so, I think the only way of finding all these trajectories is to essentially solve these sort of equations. You could, in principle, try to find all of this by starting from local operators and just analytically continue down. It just would take you forever. And sometimes efficiency matters. So here is what they all look like. So once you have this, you can start running numerics. So you use your perturbative solution to find the starting point, and then you run up numerics to check what happens non-perturbatively. And what happens non-perturbatively is that everything becomes a mess. So I try to show you some pictures here, what happens. The one thing that I would like to just point out is that what happens is that different trajectories will collide with each other. Collide means that they will hit each other and then go up in the complex plane. So there is no guarantee that this spectrum is real. And this is something you would typically find when you study fission exercises. And here's another picture, tries to show this. And as you can see there, to me, if I go somewhere in the middle of these plots, this just looks unmanageable. And most likely this is unmanageable at some just arbitrary value of the couple. You simply have to rely on the numerics and that's it. But at weak coupling, there was a structure. So there's a question if we can find a structure at some other places. And of course, the only other good place to look is at strong. So let me just very, very briefly tell you what people knew before people did this. And before, everyone, as far as I'm aware, who studied strong coupling in this regime, they used the fact that they took a trajectory that went for a BPS operator. And it was noticed by Vaso a while ago by now that if you do this and you look at trajectories that pass through BPS operators, you can get exactly this sort of expression for the conformal dimension. And this is extremely nice because it's a perturbative series in S, small s. But you can also see that the lambda drops and becomes bigger, and the denominator becomes bigger and bigger for each and every order of S. Which means that the strong coupling limit and the small s limit interplace very, very nicely. So when people compute strong coupling, usually what they do is that they just take this expression and they try to compute this coefficient. And so what Basso did was that he computed all of the A's. This is called the slope function. So these are all known exactly. Then Nikolai, Fedor, and other PhD students at Kingston at the time computed the current function. So by now we know in principle all of the B's. No one ever calculates the next order because it becomes extremely messy. So there's no closed formula for all the C's and the B. But you can fix most of them, as I think Shai mentioned, by quasi-classic methods. So that fixes the subset of them. And then we recently computed this one numerically. So this is how people have fixed strong coupling at the moment.
For 5 minutes.
Perfect. And if you do this, you can then simply invert all these formulas, and you can find what S looks like as a function of delta as strong coupling. And this is how people can compute usually delta equals to 0. Of course, people did this also from string theory using other methods. But the most efficient way of finding the high order to this correction right now, I would say, is using these methods. So we tried to ask ourselves what would happen if we do this for trajectories that doesn't pass through the BPS operator. And we took our collection of data and we just ran it as a strong coupling. And here is what happens. So here's a plot of spin for length equals to 4. So this is essentially the analogy of the plot I showed at the very beginning of the talk, but now for S instead of for the conformal dimension delta. So here is this perturbative regime of weak coupling, the sort of ABBA regime, where I can use the equations I showed you to find the spectrum. And let me just show you the sort of notation here. So here's the first horizontal trajectory, there's the second horizontal trajectory, and here's also actually this reflection area that I mentioned very briefly. So the point is that at weak coupling, these notions exist. There is no such thing as a first horizontal or a second horizontal trajectory if you go to intermediate coupling. This is a weak coupling notion. If you go to intermediate coupling, there's just a spectrum. And everything will mix, everything will collide and become a mess. But what happens when you run into strong coupling is that you see this beautiful reorganization where the spectrum becomes these discrete set of lines again. So this looks precisely what you would expect from sort of stringy spectrum that emerges at strong coupling. And so you can ask yourself, okay, this looks nice. Can I learn anything about it? And we try. So just to say that here's the picture, this one state is the thing that people computed before. So we took our data, we fit it against this, and we found that it's a perfect match for this simple formula. So here delta is simply an integer. It's 0 for the first trajectory, it's 2 for the second one, 4, and so on. And the subleading piece is this simple thing that if you look at it, you go delta plus 2, you will say some Casimir at some point. That would be your hope. And so this is exactly what we found for numerics. But we have no idea how to do analytics for it. So if anyone knows how to do it, I would be interested, just for the sake of academic curiosity. So let me conclude and give some quick outlook. So what I told you about is that the QSC simplifies very, very much when you look at these horizontal trajectories. And at weak coupling, we seem to have found a set of equations that allows us to solve this and actually compute what the spectrum looks like. And when we run this up to strong coupling, we see the emergence of some sort of string theory spectrum. It looks very similar to a Wilson loop for the people who have studied this most. So what would be fun to do? Well, there's always fun to extend. So there's ABGM, theoretically it's free. If you look at what people did for Wilson loop for ABGM, you look at their expressions, you will see that this seems to have massless modes in there. You could hope to compute something using Mirror-Shapiro, strong coupling. If you want to try to push conformal registry, you will have to try to do OP, hexagon, conformal bootstrap, or anything like this. And if you're ambitious, you would try to map this to any sort of non-local operator calculation. And hopefully this will, in the end, lead to some sort of synthesis between different things. So, thank you very much.
Don't want to do all of them, but.
Well, the string regime where you have the clear foundation and the spectrum.
Yeah.
What that, like, can I think of some classical string solution, or you said the wheels from it?
Oh, yeah, you can try to think about classical string series, for example, but
It's like energy zero.
no, you would have to compute in a different regime. But it will still be a short string. That's to the best of my knowledge. It would be challenging. To be fair, I don't know. I don't know how to do this in a good way. But if you know, that would be amazing.
Any other questions? I don't see any hands, so let's thank Simon again.